Very good afternoon, Ahmed. We'll start in next 1 minute. Okay, since it's the time, so we'll start. Uh, the remaining students might join after a while. So let's have a look that what we have completed in the week 5 of this particular week, in this particular technique of material characterization course. In this particular week, we went through the concepts like reciprocal lattice. We also studied about the relation between the reciprocal lattice, real lattice, and the diffraction pattern, like the interrelation between them. Then we studied about the Ewart sphere, single crystal and polycrystal diffraction pattern, how they differ from each other. We also talked about the selected area diffraction, and then the structural factor, zone axis, and the indexing the diffraction pattern. We have studied the method how we can do it. Okay. Even though we have not studied this in the detail yet, but for the beginners, this is more or less sufficient what has been taught in the indexing the diffraction pattern. Then we discuss about the dislocation contrast, like under what condition dislocations will also give the contrast in the TM images. So these are the list of the concept that has been covered in the week 5. So before I proceed further, I would like to ask you if you have any doubt in this particular week, whatever the concept that has been covered, or not only this week, even in the previous week that has been covered, please feel free to ask me. You can always post your doubt on the chat box, or you can also feel free to mute yourself and interact with me if you have any doubt. If not, we'll proceed further. We'll discuss few concepts. Based on those concepts, we'll try to solve few questions. Okay, let's move ahead. So right now in front of our screen, this particular pattern, this is a diffraction pattern. Ewart sphere, I think you prefer. Ewart sphere need, I think, more clarification. I think you want to ask about the Ewart sphere, right? Okay, yeah. Yeah, we'll okay. Let's discuss about that also. Here is the evolved sphere. We'll discuss about it. So this is a diffraction pattern which we are seeing. We know that we are able to see the diffraction pattern, which is correspond to the reciprocal space. Each of these particular spots, they are reciprocal lattice point. Okay. So we know the diffraction is which is there, which is always is happening in the reciprocal space. Diffraction is we can visualize in the reciprocal space, right? So these are the each spots will correspond to the plane. So in the real dimension, if we talk about in real space, if we talk about, if I have a plane in the reciprocal space, it will convert to the point. So the dimensionality, we can see the plane is 2D information. We are converting it to the point, that is a one dimension information, or zero dimension, sorry. We are reducing the dimensionality. Now, this is nothing but a diffraction pattern. So the diffraction we obtain if the Bragg's law, the condition has been satisfied. We know the n lambda equal to 2d sine theta. We can always take n to be the 1. So lambda will be equal to 2d sine theta. And when this condition is satisfied, we can say that the diffraction occurred and our plane is giving the diffraction pattern. Now, as Ahmed asked about the evolved sphere, so what is evolved sphere? See, you have the real lattice. You can convert them into the reciprocal lattice. So consider that just like the real lattice is having 3 dimension space, like the point in the 3 dimension, the reciprocal lattice is also having the 3D lattice in the reciprocal space. Now see, n lambda equal to 2d sine theta. This is a Bragg's law, which we can see that we can say that in the real space. Evolved sphere is one of the way to tell that this is the Bragg's law in the reciprocal space. For example, let me tell you that if a particular point that is like, I saw the lattice, this is my direct beam, where the ki, the wave vector, the magnitude of the wave vector is nothing but 1 over lambda. This, taking this to be the radius, I draw a sphere. It's not the circle, remember, it's a sphere. Now since it's a sphere, it's having 3 dimensions, like entire space it's covering. Whichever the lattice point that is intersecting this sphere, they will undergo the diffraction. And then we will see that, okay, those diffraction spots will be visible in our diffraction pattern. So evolved sphere, see this condition that, okay, the point is touching the evolved sphere, and that's how the Bragg's law is satisfied. This is the Bragg's law condition in the reciprocal space, that it should be onto the evolved sphere. Bragg's law in the real space, n lambda equal to 2d sine theta. Bragg's law in the reciprocal space, this vector is g star hk, and if the point is lying onto the evolved sphere, if any particular plane that is lying on the evolved sphere, then we will say that, okay, that is a Bragg's law. More or less, this is what we have studied in the evolved sphere. See, there is a more and more, like more informations are there. For example, in the class we have studied that the lattice point in the reciprocal space, it sometimes it get elongated or it get diffused a little bit. In that case, what will happen, the point which was not touching the evolved sphere, still it will undergo the diffraction phenomena, because the lattice point, the reciprocal lattice point, has been diffused, or we can say that it's little bit elongated in certain direction. So in that case, this will also undergo the diffraction phenomena. So this is usually happen when it happen that when this the reciprocal space, the reciprocal lattice point, from being the point, they take some dimension and they elongate in one of the directions. When it happen, it will happen if you keep on reducing the size of the crystal. If you keep on thinning your specimen, the thickness of the specimen, if you keep on decreasing it, these points, instead of being the point, they will start to show the rod-like structure, cylinder type. So the points which is not on the sphere, onto the evolved sphere, they will also undergo the diffraction phenomena. Okay, so if you keep on thinning your specimen, you will get more and more diffraction points. This line which I have said, you can use it to solve one question which is already there in the assignments. Okay, so now KD is a diffraction vector. Okay, Ki is incoming beam electron vector, and this is the diffraction vector, and this delta k is the difference between them. Okay, this vector. So, Ahmed, let me know whatever I have told you about the evolved sphere, is it clear or not? And if you have any doubt in the evolved sphere part, please let me know. Everyone, any doubt in the evolved sphere part, let me know. Okay, okay. So this is how, in general, where can we use evolved sphere? See, for example, let's get to the practical application of it. Just now I told you that the radius of the evolved sphere, which is magnitude of ki vector, is nothing but the 1 over lambda. Lambda is a wavelength. It is a wavelength of the electron beam, right? Now, consider that our d spacing is nothing but something like 2 angstrom, right? So, d spacing more or less like this. If we reverse this in the reciprocal space, this is in the real space. In the reciprocal space, the d spacing will become 1 by 2 angstrom inverse, that is 0.5 angstrom, this much. Now, see the wavelength. The wavelength of the X-ray is around 1.54 angstrom, more or less close to the d spacing in general of the atom, right? In general, for crystal, if we are talking about for the X-ray. While if I keep on decreasing the size, instead of X-ray, if I am using the electron and that too in the TM, 200, let's say 200 keV, my this wavelength will go by the order of magnitude. They will decrease by the order of magnitudes. Correspondingly, so 1 over lambda will increase very much, right? They were comparable, so their reciprocal space is also comparable. But here they are not comparable. See, they are very large. The lambda is very small compared to the d spacing. So in the reciprocal space, if we see, so our 1 over lambda will be quite large. Let me tell you some rough estimation that the reciprocal space for the evolved sphere, the radius, will be 200 times more than the d spacing, this 0.5 angstrom inverse in the reciprocal space. So what will happen in that case? In front of that particular lattice, which is the reciprocal lattice is there for corresponding to your specimen. In front of that lattice, your electron beam, the radius of this, it will be very large. Now if I try to draw this sphere of this, if I try to draw a sphere, evolved sphere of this, what it will tell that all these things, see, we know that the section of the large sphere, the small section of the large sphere is nothing but a plane, right? A flat plane. So all of them, since they are touching the evolved sphere, they will satisfy the Bragg's law. Now, since they are satisfying the Bragg's law, so we can say they will contribute to the diffraction pattern. So this is where the evolved sphere, the construction of this evolved sphere will help you to know that, okay, like what is the rate, how much wavelength you should use, what is the diffraction pattern you are getting, and you can relate them with your real space. Okay, so evolved sphere is nothing but a condition for the Bragg's law in the reciprocal space. Just like n lambda equal to 2d sine theta, we say in the real space, the reciprocal space we say that if a reciprocal lattice point is touching the evolved sphere, they will satisfy the Bragg's law. This is one of the conditions of the Bragg's law to satisfy. Okay, am I clear, Ahmed? So this is how we can use it. Larger the larger the sphere, you can use the diffraction pattern. You can get the diffraction pattern easily. So, so based on this discussion that we have made till now, if you have any doubt, please let me know. If not, let's try to answer a few questions. The question number one, we have to choose the correct statement. Let's see one by one. The first one, the reciprocal of the reciprocal lattice is a reciprocal lattice. The reciprocal of the reciprocal lattice is a direct lattice. The reciprocal of the reciprocal lattice is a diffraction vector. The reciprocal lattice of the reciprocal lattice is a structure factor. It's very confusing, but the question is very easy. What do you think? What will be the right answer? See, when we are going from real lattice to the reciprocal lattice, what we are getting in that case, how we are going that? If in the real lattice, if the lattice parameter is a, b, and c, then in the corresponding reciprocal lattice, the parameter will be 1 upon a, 1 upon b, 1 upon c. So let us say we are denoting them by the 1 upon a, we are denoting by the a star, 1 upon b, b star, and 1 upon c, c star. If I want to go back to the real space from the reciprocal, what I'll do? It will be the same operation will be applied, right? So it will be 1 over a star, 1 over b star, 1 over c star. What is this? This is a reciprocal and this is a real. So the reciprocal of the reciprocal lattice, the reciprocal of the reciprocal lattice is nothing but a real lattice, that is a direct lattice. Clear? So we were having the reciprocal lattice. So what reciprocal of the reciprocal lattice we want to find? So this is the reciprocal lattice. And we did the reciprocal of that. What we got? We got the real lattice. Simple. Clear? So this is the right answer here will be the option B. Clear? If any doubt, guys, let me know. If not, let's move to the next question, question number 2. This concept is been introduced by the professor in the first class of this particular week. So what it say that, let us say that this is our plane where we are seeing the diffraction spot. Now, let's say the beam is coming from this, like this, having the length of L. The wavelength of the beam is lambda. The distance, let's say right now we are concerned about this particular spot, In that case, we can say, let's say that the distance between them is r. Okay. So, and let's say that this is corresponding to the one of the plane in the real case. We know every lattice point in the reciprocal space correspond to the plane in the real crystal, so it is corresponding to the plane. We can say that HKL. Let us say this plane has a d spacing of d. So the entire the mathematical formulation, the way we did in the class, is that what it say that lambda, it will relate this parameter lambda, L, R, and D. So lambda times L will be equal to R, D. This is a formula that has been formulated. It's very significant, it's very useful formula for the entire diffraction pattern analysis in the TEM, what it say that, see, lambda is constant, L is a camera constant. For different mechanism, magnification, you will get different L value. Okay, that you can ask the operator. Okay, this magnification I did. Tell me the L value. So this entire thing you already know. Lambda is because you know how which beam you are using, which electron beam you are using, which energy electron beam you are using. Lambda you know. Yes. So Uday is telling the right answer is lambda times, yeah. That's right. Right answer is option B. See, you know already these things, right? Very good, Uday. So we already know this thing. So what is unknown right now? R and D. R you can find by the reciprocal lattice, the distance between the direct spot and the diffracted spot. Since you are able to find this, since you are able to find this from the reciprocal lattice, so what is left over is the D. So corresponding to each plane, each diffraction spot, corresponding to each R value, you will get the D spacing. So from this D spacing, you can find what is your crystal. Okay, so this is the person who is studying about the TM, one must aware about this particular equation. So very good. Uday has already told the answer is L lambda by D. If any doubt in this question, let me know. If not, let's move to the next question, question number 3. Now this thing we have discussed in the while well in that particular theory discussion part, right? So now in electron diffraction, so we are confined to the electron diffraction, the first one, a greater number of diffraction spot appear for the thinner crystal, a greater number of diffraction spot appear for the thick crystal, a greater number of diffraction spot appear for the larger interplanar spacing. Very good, that's right. Right answer is option A. So we also found the reason for that, like if the thickness is decreasing, the relaxation in the Bragg's law will increase. It is happening because we know that evolved sphere, like it is happening because the spots, the lattice points which are near to the evolved sphere, they are also contributing. This will also contribute because they are diffuse little bit. Now they will touch the evolved sphere, and due to that, due to the reduction in the thickness, due to this relaxation, each lattice point which is close to the evolved sphere also, they will also going to participate in the diffraction. So you will get more diffraction spot in that case, right? So that's how the answer is A is right. Second one is stating that the larger number of the diffraction pattern obtained when the thicker crystal will reverse this particular phenomenon. So in that case, you will get a sharper spot. Also, the number of spot will be less. Okay. So that's how we have solved this question number 3. If any doubt, guys, let me know. If not, let's move to the next question, question number 4. Here, the question says that, question is asking what is the radius of the evolved sphere. Sorry, if the radius of the evolved sphere is given, what will be the electron wavelength? It's very easy. We know that the radius of the evolved sphere, which is k, is nothing but a reciprocal of the wavelength. So we can find that, and the radius of the evolved sphere, that is k, is given as 250 nanometer inverse divided by 1 over lambda. So one can easily find the value of lambda. What it is? So what we have to do is 1 over 250 nanometer inverse. So we'll get the value of 4 into 10 to the power of minus 3, since it is a nanometer inverse, it will become nanometer, the reciprocal of that. So one can write it 0.004 nanometer, or one can express it in the Armstrong or whatever the unit that has been specified in the question. Okay, so this is how we can solve this question number 4. You will find the similar questions, similar type of questions in the assignments. Let's move ahead. Let's move ahead to the next question, question number 5. The question number 5 is more or less related with the week 4 question that we have solved together. Let's have a look. The bright field TM image form when, under what condition bright field will operate? The direct beam and all the diffracted beam electron, the direct beam only, and eliminate all the diffracted electron. All the diffracted beam, all of them. See, this is our specimen. Electron beam is going. One is directly going. It will directly penetrate through the specimen and pass. Few of them will diffract. It will go in the different direction. While for the bright field, if we are talking about the bright field, we are only using the direct beam. That is this one. Okay, very good. The right answer is option B. Right. We are only using the direct beam. This diffracted beam we are not using at all. When we will use them in the dark field. In the dark field, we will use the diffracted beam. Right. So that's how, like, this is more or less related with the week 4 content that has been discussed. So just for the revision, I put it here. Okay, let's go to the next question. I want all of you please answer this question. It's very easy. The real and the reciprocal lattice are inversely related, having a cube relation, equal, have a logarithmic relation. Right? Very good. The right answer is option A. They are inversely related with each other. If in the real it's A, B and C, in the reciprocal they will contribute over 1 over A, 1 over B and 1 over C, and vice versa. Very good with that. The right answer is option A. Let's move ahead. Now, this is something, the concept which we discussed with respect to the X-ray, evolved sphere in the X, and when we are using the XRD, and evolved sphere when we are using the electron beam. For electron diffraction, we are limited to electron diffraction. The evolved sphere radius is, the first one, very small compared to the spacing of the reciprocal lattice point, approximately equal to the spacing of the reciprocal lattice point, very large compared to the spacing of the reciprocal lattice point, not defined for the electron diffraction. What do you think? They are asking us about the radius of the evolved sphere and how much, like, how it is big, larger, smaller, or equal with respect to the reciprocal lattice point. So here we saw that the reciprocal lattice points, the spacing between the reciprocal lattice points are more or less like this, not too much, while the radius is very large. So the evolved sphere will be very large compared to the reciprocal lattice point. Right? It won't be the option D. So not defined for the electron diffraction. No, we cannot say that. It's defined for the electron diffraction. So see, reciprocal, the radius of the evolved sphere is nothing but 1 over lambda. And for the electron beam, we know that lambda is very low for the electron. While for the X-ray, the lambda is more or less like 1.54 if we talk about the copper. So more or less it will be like this, right? So what we can say, if we go to the reciprocal space, where in the real space the dimension was like 2 angstrom. So in the reciprocal space the dimension will be 0.5 angstrom inverse. While if we talk about the radius of the evolved sphere, it will be more or less like 200 angstrom inverse, 200 250 angstrom inverse, which is very large compared to the lattice spacing. So what we'll say that very large compared to the spacing of the reciprocal lattice point. Okay, so evolved sphere will be very large compared to the spacing of the reciprocal lattice point. The right answer is option C. Right? Any doubt in this thing, guys? Let me know. Okay, since there is no doubt, let's move to the next question. Question number 8. Now over here, in order to answer this, like let's read the question. The finite size of the diffraction spot rather than the perfect point is primarily due to. So what the question is asking, let's understand the question. Where is that particular figure? Yeah, over here. See, let's see this particular diffraction spot. It's more or less like this much size. Instead of being the dot, instead of being the perfect, what we say that if diffraction is happening, it should occur at the particular d spacing, a particular theta where the Black's law is satisfied. But we are getting the finite size instead of being the point. So why it is that? What is the reason for that? Let's see the length averaged in the TM, the use of the convergent electron beam, the relaxation of the Bragg's law for the finite crystal lattice. D. Inelastic scattering event. Now one can also relate it with the XRD, how? That in XRD also one should get how it should be like that. It should be very sharp peak when the diffraction phenomena is satisfied. While in the real case, what we are getting is something broadness will be there in that peak. So even like this is the angle at which it should correspond to the Bragg's law. So only the intensity should occur at this particular angle itself, but it is also occurring at the another. Okay, it is because of the relaxation in the Bragg's law. It is not due to inelastic scattering. It's not due to the convergent electron beam or the lens aberration. It is due to the relaxation in the Bragg's condition for the finite crystal lattice, crystal thickness. Okay. So the thing is that if we talk about the X-ray, we say that okay, like all the lattice planes, since the size is smaller, the size is confined, all the X-rays which is diffracted, they will not be able to cancel out with each other if we go just little bit away from the Bragg's law, and they will undergo the diffraction. They will show that. Similar type of phenomena is also happening in the case of TM, where we are seeing that the beam, the diffracted beam, is not a single point. Rather, it's quite large, little bit. The spot is quite diffused. So it is happening because of the relaxation in the Bragg's condition. Okay. While if instead of finite, if we use infinite crystal, the size of the crystal is infinite. In that case, you will get a spot, a single spot. There won't be any diffused ring. There won't be any broadening in the XRD pattern also. It will be straight line. Okay. So this is how we have solved this question number 8. If any doubt, let me know. If not, let's go to the next question, question number 9. Okay, this is interesting. Why this required? Actually, Ahmed, I not got the question. I think you might be referring to the 8, question number 8. Yeah,
Hi, good evening.
yeah,
Here, finite site, the diffusion spot is primarily due to the relaxation of the Bragg condition for a finite crystal thickness.
yep.
Why the relaxation? The reason or the purpose of the relaxation, or purpose of this, the benefit where we are getting, uh, which stage it is in the process it is happening. This is
Uh, Amit, can you repeat again just once more time? There is some noise was there.
yeah. Here, the answer we got it because this in the whole process of the TEM, what is, why this is relaxation is needed. Relaxation of the Bragg condition is needed. Theoretical or it is anything it is related to practical.
Yep.
It's like assumption part or it is really when we are operating to that 10,
Hmm.
these are all what a user can face and its need for the application. Where the application point or where this is user point of view. What is the purpose of this relaxation of this Bragg condition of the finite crystal thickness?
Yeah, very good
These are
question.
all.
Yes. So actually, we don't need relaxation. What we need, see, if we want, say, initially we talked about the fact that initially we talked that using this reciprocal lattice point, we'll go to the real space and we'll try to find the d spacing. In order to do that, you need to find the distance between the center spot and the spot which is little bit another diffracted spot, right? So since it is an imaging tool, since now we are not doing the XRD, we are trying to find the d spacing using this particular TM. So what is happening that in this particular images, you will always find some error associated with your measurement. So like if you give me, I might, instead of going to the exactly center, I might go a little bit away. It might be possible that you are like exactly at the center, you are able to spot it, but there will be always some error will be associated with that. So it's not that we required it, it's that the way the specimen is, the specimen, if you keep on thinning the specimen, so what is happening that, for example, let us say this is my lattice plane. So at the Bragg's law, they all satisfy the Bragg's law. Exactly, where the Bragg's law should satisfy, they all satisfy the Bragg's law. They are giving the very high intense peak. Let's say we are deviating very little bit from the Bragg's law. In that case, what will happen? This one, the part difference between them will not be integral multiple of lambda. It will be slightly away from each other. They will be slightly away from each other, right? So what will the first one will try to do? First one will try to do, okay, let's say the first one is having the wavelength of some particular wavelength, let's say lambda 1, and the second one is having the wavelength of lambda 2. They are slightly deviated, so first one will try to find the wave x-ray which is exactly in 90 in the phase difference of n lambda. Okay, it will try to find a lambda like a beam having the wavelength lambda 3, with which if we separate the lambda 1 we will get the puff. So what it will, so this is deviated by a little bit, again the second one will again be deviated a little bit, again more. So keep on doing so. It might be possible till certain depth of the crystal you will be able to find a lambda 3 which is exactly in the phase of, actually in the, if we separate them, the part difference will be n times lambda. So do the lambda 2 also will do, it will try to find the lambda 4 which will be exactly away, exactly in the integral multiple of n lambda. Now let us say, so this will take the certain width of the specimen. Now let us say that your specimen thickness is fixed. You are not you're not giving these things. Okay. So in that case, what will the cancellation will not happen. Okay. In that case, that's why you are getting the intensities keep on decreasing. if see instead of lambda 1, what it will do, since they not satisfy the Black's law, what it will do, or instead of n lambda, they will find that the integral multiple of lambda by 2. So now what will happen, this first one and third one, they will try to cancel out with each other, they will cancel. Second also try to cancel with the lambda 4, and where it found that it's not the integral multiple of lambda, it's the path difference is n times lambda by 2. In that case, lambda 2 also be cancelled out. Keep on doing so, it will cancel out. But if you are not giving sufficient lattice plane, in that case it will not cancel out. It will give some diffusion, like the Bragg's law, the condition from the, even though these are also contributing certain intensity if they are not cancelled out. So that's why instead of getting the sharp peak, what you are getting is the broadness. So like the theta, where it was not supposed to diffract, there also it is diffracting. Now the similar concept, like since now we are using the n lambda equal to 2d sine theta, this concept is itself is we are using in the XRD. Same Bragg's law we are using in the TM also. So now what is happening? Again, a slightly deviation from the theta, they are not able to cancel out. The path difference is not equal to cancel out if you keep on thinning the specimen. So there will always be some relaxation because of the dimensionality. Okay. While if I tell you that if you make the crystal very large, infinitely large, in that case you will not find the diffuse ring. You will find the central spot, or in the XRD you will find the straight line at particular angle, because in that case the first lambda 1 will be able to find the lambda 2 or lambda 3 which is out of the phase of the lambda 1, right, and they will cancel out with each other. So this is how the entire process look like. We don't desire these things, the diffused, the relaxation in the Bragg's law, we don't desire. More or less, if you can eliminate it, then it is beneficial for you. You will get a very exact, precise lattice parameter which is there. One way people say that it is useful, if you are wanting like how it is useful. So we can say that, let's say in the specimen there is a lot of defect is present in your specimen, dislocations or the point defects. In that case, what will happen? Again, the deviation from the Bragg's law will happen. The defects can deviate things from the Bragg's law, or it can also support the Bragg's law. In that case, also diffusion. So that's why when we talk about the XRD, full width at half maximum, it's talk about the crystallite side, it's talk about the defect which is present in the specimen. We say the broader the peak in the XRD, broader is the, like more is the defect in it. Same thing, in the same way, we can talk about the diffraction pattern which is there in the TM. More it is diffuse, it means that that particular set of plane is more we can say that more defected, right? So if you want application, I can say that okay, that you can some certain action, you can quantification you do, you can get some rough estimation that what might be the defects. Okay, so if it is clear, let me know. If not, then let's discuss it even more. It's clear? Great. Okay, so this is a question number. Question number 8 is done. Yeah, let's go to question number 9. Yep. Now, first one, true or false? True and false. The camera length L in the equation this is a fixed physical distance in the TM column. Is it a fixed distance, or will it is variable? If I keep on changing the magnification, the camera length L, will it change or it will remain the same? Next, no, it's false. It will depend upon the what is the magnification you are going. Your camera length will keep on decreasing. So that's why like whenever one do this TM, they can always ask the information from the operator that okay, at this particular magnification, what is the camera length? So he will calibrate the TM before use. So he will tell okay, this particular magnification correspond to this particular camera length, this particular correspond to this camera length. So the camera length, this is not fixed, it's a variable. Okay, So it's a movable. It's not the fixed concept. So that's how the answer will be the false. Okay, I hope you got it. Uh, you can also use this the discussion that we have made to solve a question in the assignments. There is one assignment question based on the similar concept. Now let's go to the next question, question number B. The reciprocal lattice of the crystal is independent of the crystal structure and the symmetry. Reciprocal lattice, they are telling that reciprocal lattice, the question is saying it doesn't depend upon the structure and the symmetry. Very good, Ahmed, it's a false. Right? It depends. They are just the reciprocal of each other. If one will increase, another will decrease. Now the third one. In the evolved sphere construction, diffraction occur only when a reciprocal lattice point lie exactly on the sphere. Let us say we are talking for the finite crystal. In the evolved sphere construction, the diffraction occur only when the reciprocal lattice point lie exactly onto the sphere. If we talk about the, let's talk about the infinite, in that case it will be the true. We told that lying onto the evolved sphere is a condition for the diffraction to occur. So for the infinite crystal, where there is no diffused in the reciprocal lattice point, in that case what we'll say that okay, it is a true. While for the finite crystal, it will be false, right? So the right answer for this is true if you are talking about the infinite crystal. The last one. The diffraction pattern from a single crystal consists of the continuous ring. What do you think? There is an entire lecture we dedicated to this particular concept. How the diffraction pattern for the single crystal and the polycrystal vary from each other. It's a false. Very good there. Instead, it will be the discrete diffraction point. Right? So that's how we have solved this question number 9. If there is any confusion, let's on that particular last part, then we can clear over here. Here we can see that the first one is a diffraction pattern for the polycrystal. Second one is for the single crystal. In the case of polycrystal, you are getting the diffuse ring. In the single crystal, you are getting the discrete points, diffraction point. Now, why it is happening? In the single crystal, we know that a particular crystal is having a particular orientation. So the grain is oriented only in the one direction. So the diffraction, if the diffraction condition is satisfied, only that particular grain is going for the diffraction phenomenon. While if we talk about the polycrystal, they are the different grains. They are rotated by each other with respect to each other, right? Now this, let's say this grain also satisfy the Bragg's condition. This grain also satisfy the Bragg's condition for the particular electron beam. Both of them will give the diffraction pattern. Now since their orientation are different, so the diffraction pattern, let us say the grain 1 is giving diffraction pattern something like this. This is a beam, the first one, second one, third one, fourth. So grain 1 is giving this. So the grain 2, since it is oriented a little bit, so what it will give something like this. Okay, I should have put over here instead of here. So you have got like it is rotated. So now instead of 2 grain, if we have multiple grain, more than like 50, 20 grain satisfying the Bragg condition, then in that case what we'll say that instead of discrete point, they will form the ring. They will keep on forming the ring. They form continuous ring. So this is how a polycrystal will look like. Now let us say you have a phenomena where you can heat the specimen, polycrystal, and you are keep on increasing the size of the crystal, grain size is increasing. So in that case, what will happen? Your ring will start to show some discrete points instead of the continuous ring. The polycrystal will turn slowly towards the single crystal. Okay, so the diffraction pattern more or less will be like this. Or we can say that if I have a single crystal and I keep on deforming it, so in that case, what will happen? This discrete diffraction spot will this start to form the ring. Okay, so this is how it is. One thing, a d-spacing of a particular plane will be the same over here. This correspond to the 111, let's say. So this is the radius. This r is nothing but the radius, like corresponding to the 111 plane. So again, using the formula that d times r, lambda L, you know, r you can find from here. You can find the d. Okay, so this is how it is. So even for the polycrystal, even for the single crystal, you can do the same things. Now, let's try to solve few questions. For a very thin crystal, if the crystal is very thin, the reciprocal lattice become extended into, how it will be extended? Let us say this is your size of the crystal initially, before you thin it down. The right answer is option C, very good. Right, it will turn to the rod. Let us say corresponding to this particular crystal size, one of the lattice point, one of the reciprocal lattice, let's say it is like this, or let's take few more. If I keep on thinning it, in that case what will happen? This will try to elongate. This reciprocal lattice points will try to become like a rod. So now you can see that if I draw a evolved sphere over here in the case 1, and if I draw the evolved sphere in the case 2, in which case I will get more diffraction pattern, more diffraction spot, case 1 or case 2, more diffraction spot, in which case I will get case 2, right? Because they are elongated, they are going to touch the evolved sphere and they will satisfy the Bragg's law, so more number of lattice points. So if you keep on thinning the specimen size, your reciprocal lattice point will be elongated along the side which is thinner. Okay, so that's how it is. So the right answer is option C. Okay, let's move to the next question, question number 11. The question says that the transition from the ring pattern into the spotty pattern in a polycrystalline sample indicate. What does it indicate? The question is that our diffraction pattern is changing from here to here, from first to second. That is from the ring pattern to the spotty pattern. What does it indicate? First one, an increase in the number of randomly oriented grain. Second, a decrease in the number of the grain or the onset of the preferred orientation. Very good, Amal. The right answer is option B. If you keep on hitting your specimen, if you keep on increasing the grain size of the specimen, in that case what will happen, that the number of grain is decreasing. So there, the randomness which was there in the grain is decreasing. So instead of being the ring, they will try to form the diffracted pattern, which is like the more or less resemble to the single crystal diffraction pattern. Very good. The right answer is option B. Okay. Let's go to the next question, question number 12. First one. The diffraction pattern from a polycrystalline material with a very large number of randomly oriented grain will show the incomplete ring. Large number of randomly oriented grain will show the incomplete ring. Incomplete ring, they are meaning that you will get spots, distinct spots. What do you think? False, right? Very good. More is the randomness in the grain, more larger, larger is the number of grain, more is the number of grains. They will tend to form the circular. They will tend to form the ring type of pattern, not the spot type of pattern. Okay. So the question about first one is done. Let's move to the next one. The spotty ring pattern. Spotty ring pattern means the ring is there. It's more or less like a ring, but you are getting something like discrete points. The spotty ring pattern occur when there are the limited number of diffracting grain in the selected area. You selected a small area from where you want to do the diffraction, and you're getting the limited. Very good, it's a true. Right? Smaller, the less number of grain you are using for the diffraction. So what is happening that the diffraction will not be the ring, it will form the discrete points. Very good. Let's move to the next question, question number C. The symmetry of the crystal structure, cubic tetragonal, is not reflected in the symmetry of the diffraction pattern. What do you think? The symmetry of the crystal structure, it will be reflected in the diffraction pattern. So it's a false. The angular symmetry will be maintained. If you are seeing the threefold symmetry in the cube along the 111, if you also take the diffraction pattern with 111 being the zone axis or the beam direction, you will again find the diffraction pattern which will be having the threefold of symmetry. If in the cube you are getting the fourfold symmetry along 100 in the real crystal, in the reciprocal lattice, in the diffraction pattern, if your beam, if the zone axis is along the 100, again you will get the fourfold symmetry. Okay. So they are symmetry equivalent. The last one. The epitaxial film, the diffraction pattern can transition from the ring to the spot as epitaxial perfection increases. True, very good. What is epitaxial film is that, like, you take one substrate on which you are growing the crystals, like on which you are growing the crystal. So what will happen that with the slowly, since it's very at the initial stage, the d-spacing will be little bit diverted from each other. Okay. While if you keep on growing, they will tend to form the more single crystal orientation. Like it's like a this is the bottom up approach to create any structure, right? So in that case, we are getting the diffraction pattern. Instead of ring, from ring, it will transform to the spot. Okay, very good with that. So the right answer is option D. With that, let's move to the next concept. The concept is about, again, the same thing more or less we are going to discuss for the, now we are talking about the selected area diffraction pattern. Okay, let's say you not inserted the SID detector, sorry, aperture. you are getting the entire the pattern from like wherever the illumination is happening, wherever you are putting your electron beam onto the specimen, that area will undergo the diffraction and you can see the diffraction spots. This is the direct beam and remaining are the diffracted beam. This is for the single crystal. Single crystal are getting the discrete diffraction pattern. Now this is for the polycrystal. Polycrystal, but not very large number of grains. How many grains are there? 1, 2, 3, 4. More or less 4 grains are there, which are rotated, which are distorted. But they once they since they are satisfying the Black's law, will get something. You can see that more or less this is also trying to form the ring. If I try to connect each spots, it will try to form the ring. Now, instead of 4, what you are doing in that same area, the number of grains has again increased. For example, there is a technique like you can deform the specimen. Equichannel angular pressing, ECAP, there is a technique by which you can deform your specimen. You can increase the number of grain in that. Okay, so by that what will happen? We can see that instead of being the spotty pattern, it will become a ring. So consider it like this. Single crystal, you deformed it a little bit. You made 3 to 4 grain, it will become the spotty pattern. From spotty pattern, you again you are deforming it further and further. You will get the ring type of pattern. This is more or less selected area diffraction pattern. You can select a particular area from which you want to obtain the diffraction. So now, for example, let's say that you are telling that I am not interested in the ring pattern. I want diffraction pattern more or less like the single crystal. In that case, what you will do? You will make sure that you will focus on one of the grain. You will select the area in such a way that this is what we call the selected area diffraction pattern. You will select the area, and now you will try to form the diffraction pattern only by using that particular selected area. Okay, this is one of the concepts that has been discussed in the class. Next, we discuss about the FCC and BCC. We discuss about the structure factor. See, it is very well possible that right now, like we talked that if if orientation is satisfying the Bragg's law, the diffraction will occur. Bragg's law, then it should diffract. But even though if it's satisfying the Bragg's law, if the structure factor is 0, then no diffraction. Like you won't see the intensity. So along with the satisfying the Bragg's law, it should also satisfy the structure factor. And if the structure factor is non-zero, then only you will get the diffraction pattern. Okay. So now what is the structure factor? So the structure factor is given by F times. Okay, it's not very clear over here. Better I write it somewhere. It's a capital F. This is structure factor where F is a atomic scattering factor. The small f is an atomic scattering factor. It is like the small f is telling that how much of one single atom will scatter. The structure factor is telling that how much of one particular unit cell will scatter. Atomic scattering factor talk about the only one atom. It talk about the unit cell, how much it's going to scatter. So since we are talking about the unit cell, we have to also take into account that the plane HKL. So what will happen that an XYZ are the atomic position. So we got to know that this entire thing, it talk about that scattering from a one particular unit cell. Small f is talking about that scattering from a one single atom. Now let's try to, now here it is. Now if we talk about the FCC and if you talk about the BCC, how this factors is going to change. So here, in the FCC what you will do, you will just put the value of position, okay. So in that case what you will you will get to know that at the end it will entirely depend upon the H, K and L. If H, K, L are the mix, the structure factor is non-zero, it is 4f. If H, K, L are unmixed, well, if they are mixed, in that case you will get the structure factor to be 0. So no diffraction pattern you will get here. You will get diffraction pattern only for this. For the BCC, the criteria is different. The BCC is telling that if H plus K plus L is even, if they are even, then diffraction pattern will be, you will see the diffraction spot. If it is odd, that particular plane will not give the diffraction spot. It is depending upon the plane. H, K and L, they are the plane, okay. So for example, let's talk about the FCC. 1, 1, 1. Will 1, 1, 1 give the diffraction spot or not? 1, 1, 1. Is it mixed or unmixed? If it is unmixed, then it will give the diffraction spot. We know 1 is odd, all of them are odd, none of the indexes are even, so it means that it will give the diffraction will be satisfied. Sorry, so the structure factor will not be 0, so it will give the diffraction. Now let's talk about the BCC. Again, 1, 1, 1 plane. What will happen here? We have to see that H plus K plus L. So H plus K plus L is 3. Now this is odd number. Since it is odd, no diffraction over here, right? Again, we are going to discuss all this, the structure factor part, more in detail in the upcoming week, where the XRD, extra diffraction theory will be discussed. So right now we only have to understand this much. Okay. Let's move. If any doubt in this particular concept, let me know. If not, let's move to the next one. Let's try to solve few questions based on this. The question is, for an FCC crystal, this is the first possible diffraction plane. This is the first possible diffraction plane. Which one will be the right one? First possible diffraction plane. Let's talk about the planes 1, 0, 0. After that 1, 1, 0, 1, 1, 1, 2, 0, 0. Very good. The right answer is option A. Right? So what is the criteria for the FCC to satisfy? FCC should be unmixed. That is, either all should be even or all should be odd. Here it will not satisfy because 1 is there. 0 and 0, they are even. Again, mix. All are odd. It will satisfy. 2, 0, 0. It will also satisfy. Right? So which one is the first possible one? First possible one is the 1, 1, 1. Second possible will be the 2, 0, 0. Okay. So instead of this, if I write second possible, then option B will also be right. Okay guys, very good. Let's move to the next question. Question number 14. The primary purpose of the selected area aperture, SAD aperture. See, I told you that using the aperture, you can select a particular area from where you can see the diffraction. So you can obtain the diffractions like single crystal by selecting in the polycrystal itself, by selecting the particular area, small area. So now let's try to answer this. The primary purpose of the selected area aperture is block inelastically scattered electron, select electron from a specific region of the specimen to form the diffraction pattern. Very good. The right answer is option B. Okay. Remaining all are incorrect. We are selecting a specific region to form the diffraction pattern. Right? Very good, guys. So the question number 14 is over. Let's move to the next question. You will be able to answer all these questions. The structural factor, capital F, that we have discussed in the diffraction determine the wavelength of the incident electron beam, the intensity and the presence of the diffracted beam for the specific HKL plane, the camera constant, the size of the selected area aperture. What do you think? What is the right answer? The right answer is option B. Right? Very good. Let's talk about the intensity, whether it will be present or not. See, if the structure factor is 4 times F, and if the structure factor in one case is 32 times F, we know that in the case 2, we'll get the more intensity because it's scattering more. Structure factor is nothing but the how much scattering is happening, how much the diffraction is happening. So more diffraction, more is the intensity you will get. Less intensity here. 0, no intensity. Okay. So that's how we have solved this question 15. If any doubt, let me know. If not, let's move to the next question, question number 16. The structure factor. Again, based on the structure factor only. The structure factor provides the information about first one, the amplitude of the X-ray diffracted by the crystallographic plane, the crystal lattice parameter, the atomic number of the element in the crystal, the phase of the X-ray diffracted by the crystallographic plane. Okay, the answer B is not correct, it's incorrect. It talk about the amplitude. Amplitude you can see, we always say the intensity is directly proportional to the amplitude square. Right? We always say that in the wave case. So the amplitude of the X-ray, that is the intensity of the X-ray diffracted by the crystallographic plane. Crystallographic plane HKL. For example, in FCC 110 will satisfy. 110 will be there. No, sorry. 111 will be there. It will satisfy for this particular plane. You will get the diffraction pattern, and you will say that okay, its amplitude will also be. If more is the structure factor, more will the amplitude. That is, more will be the intensity. If less, less will be the intensity. Okay. So the right answer is option A over here. The atomic number of the element in the crystal, no. The phase of the X-ray diffracted by the crystallographic plane, no. Okay, so the right answer is option A. Just any doubt in this particular one? Question number 16. Okay, so we have to keep in mind that sometime instead of intensity, for example, in the last question, I used the word intensity. One can also use the word amplitude because they are related. Okay, so with that we have solved this question number 16. Let's move to the next question. If there is any doubt, let me know. What will be the right answer for this? Question number 17. In a BCC crystal, the diffraction spot are forbidden, absent when? Let's not talk about the absent, let's talk about the present. Under what condition the diffraction spot will present? Okay, you answered D for the absent one. Very good. So the right answer is option B over here. Very good, guys. So H plus K plus L, if it is even, then the diffraction will be satisfied. This is the criteria for the BCC. Now let's move to the next question. Question number 18. The first one. True and false. SAD can be used to determine the orientation relationship between the two phases at an interface. At an interface. It is true that we can focus onto the interface also, because SAD, you know, right, we can focus on the small area. Can be used to determine the orientation relationship between the two phases. What do you think? Will be right or not? Let's see. See, let's say this is the interface. Interface between the phase 1, phase 2. This is the interface. Using the SAD, you can focus on this particular region. You can find its diffraction pattern. You can find its orientation. You can focus on this region, phase 1, you can find its orientation. You can find its orientation, phase 2. Also, you can combine all of them together. You can select a little larger area. I'm drawing the square. It's not correct. I should draw the circle. So you can select the larger area also, and you can get the diffraction pattern from all of them in together. So if someone is only interested, let's say someone did the joining of the two metal, and at the interface they want to see that what is the orientation. So in that case, you can use the SAD detector. So the right answer here will be the true. Right. Let's move to the next question. B. The camera length L is fixed physical distance in that EM column. True or false? Similar question we have done. Very good. It's a false. It's a variable term, right? Okay, now the forbidden reflection occur when the Bragg's law is not satisfied. Yeah. Forbidden reflection. See, Bragg's law is not satisfied, diffraction will not occur. So, the term when we are using the forbidden, it means that we are using from the perspective of the structure factor. Right? We are using it from the perspective of the structure factor. So, the forbidden, that is structure factor, if it is 0, even though Bragg's law is satisfied, if the structure factor is 0, then there is no diffraction. You won't get any intensity. You won't get any reflection. So this is what we call the forbidden reflection. So it is not related with the Bragg's law. It is related with the structure factor. So instead of writing Bragg's law, I should write the structure factor is not satisfied. Structure factor is 0. In that case, it will be true. Right now, it's false. It's not the Bragg's law. For the forbidden, it's a structure factor. Very good, guys. I hope this understand. If any doubt, let me know. Let's move to the last one. The structure factor depend upon the accelerating voltage of the electron beam. What do you think? We wrote the structure factor term. Did anywhere we wrote about the electron beam? No, right? Very good. The right answer is false. So with that, we have solved this question number 18. All these 4 true and false. If any doubt in any of these sections, let me know. Okay, we'll have a discussion on that. If not, let's move to the next question, question number 19. Can you illustrate again C and D? Let's see the C and D. Okay, yeah. Let's talk about the C, forbidden reflection. See, if the Bragg's law is satisfied, if this is satisfied, you will get the diffraction. Now, whether this diffraction will have the intensity, the intensity value is more than 0, equal to 0. If it is happening, if the intensity is 0, it means that you are not getting the diffraction pattern. This is happening when the structure factor is 0. If the structure factor is non-zero, in that case you will get certain intensity. If this is 0, it means that this is what we call the forbidden reflection. Am I clear for this part? So forbidden reflection is related with the structure factor. It's not related with the Bragg's law. If the Bragg's law is satisfied, diffraction will occur, that's sure. Now whether the diffraction will have the intensity to be 0 and non-zero, it will depend upon the structure factor. If the structure factor is 0, no intensity. If the structure factor is non-zero, then you will get certain intensity. Okay, so this is for the part C. Let's see the D part. The structure factor depends upon the accelerating voltage of the electron beam. We saw that it's known. The structure factor, when we wrote the term, when we wrote the term, it is like atomic scattering factor times AXP exponential of 2 pi I Hx plus Ky plus Lz. So in this entire term, this is the atomic scattering factor, it's same. H, K, L, these are the plane, X, Y and Z, they are the position, the lattice points. So in this entire term, we are not talking about the energy, we are not talking about the accelerating voltage of the electron beam. This is entirely dependent upon the structure. The structure factor is related with it's related with the structure only. It have nothing to do with the external parameters. Okay. Yeah. So Ahmed, let me know if it is clear. C and D. Okay, very good. Okay, let's move to the next question. Question number 19. The primary purpose of determining the zone axis in electron diffraction is to find the zone axis, increase the magnification of the image, understand which crystallographic plane are satisfying the Bragg's law and producing the diffraction pattern, reduce the lens aberration, calibrate the camera constant. We are finding the zone axis. The reason is that if I know along which zone, for example, let's talk about the cube. If the zone axis is 0 0 1 or 01, in that case you will see the diffraction pattern in which we have the symmetry of this, right? It will have the 4-4 symmetry. While let's say you don't know, you just know that your specimen is a single crystal and you want to find its orientation. What you got the pattern like this, you got 4-fold symmetry and you know it's a cubic. One thing is clear, that you know that it's a cubic crystal, single crystal. You got this particular thing. So what, from here you can say that it is along the 001 family, right? So you can find the orientation from the seeing the diffraction pattern. You can find the orientation. So if So, or you can find the zone axis. So the zone axis is very important. If you know the zone axis, you can comment on that, okay, which and all are the thing that is contributing to the diffraction pattern. Or seeing the diffraction pattern, you can say that what is the zone axis of it. It will tell you about the orientation. Let me tell you one example that if you are going to buy a single crystal from any company, any powder company which you, from where you want to procure your powder, you told them that I want a single crystal. They will ask that which single crystal you want, and you told that the TiO2, or let's say that the zirconia single crystal you want. Still, the information is not sufficient to them. They will ask you that what is the orientation, which orientation you want. It means that the surface which is there, the surface which is finished, this will have which orientation. Now, if you specify that I want 100 or 110, any of this, then only they will be able to provide you particular material which is your requirement. Okay, so zone axis is very important. Now, if you see that, let's say you procure this 100 specimen and you found, you pass the electron beam through it, you did the TM of it, you will get the diffraction pattern which will look like this. Okay, so this is how. So the question number 19, the right answer is option B. If any doubt in this particular one, let me know. If not, let's go to the next question, question number 20. We are about to finish. Just one more question left after this. So now here we are talking about a polycrystal BCC. Material produce the ring pattern. Okay, so let's say this is a direct beam. Now here we are having the ring. With the first ring is this one, correspond to the plane of 110. It is given, it is 110, where the R is given, R is 10 mm. Given the camera constant lambda L, calculate the lattice parameter of the material. We want to find the lattice parameter, that is A, is missing. There will be only one lattice parameter because it's a cubic, BCC cubic, right? We know lambda times L is equal to the R times D. We know this factor. R is given to us. We can find the D. From D, for the cubic, we know that D is divided by 8. D is nothing but A divided by root over H square plus K square plus L square. Whatever the D value you have here, you can substitute here. A particular set of plane is given to us, that is the plane is 110, that also you can write. From here you can find the lattice parameter. Let's try to do this. Lambda times L. The lambda times L value is given, it is 2 Armstrong mm. R is 10 mm times D. So unit will be cancelled. Now the D will be equal to the 2 over 10 Armstrong, that is 0.2 Armstrong. So you got the value of D. You can substitute over here. 0.2 Armstrong will be equal to A divided by root over, the plane is given to us, H is like 110, so we know that 1 square plus 1 square plus 0 square. So we can write it as, so A will be given by 0.2, this we can shift it over here, multiplied by the root 2 times Armstrong. Okay, now we can multiply, we can find the answer, that root 2 multiplied by 0.2. So the lattice parameter here is 0.2828 Armstrong. I can approximately write it at 0.283 Armstrong. Okay, so this is how we have to solve this type of questions. Okay, so if lattice parameter is asked, then the plane will be given to you. So using this, you just need to find the d spacing. D spacing you can find using the this particular equation. Okay. So this is all the question number 20 we have solved. If any doubt in this particular question, let me know. If not, let's move to the next question, the last question, question number 21. The last one is telling that compared to the X-ray diffraction, the TEM electron diffraction is generally less accurate for the precise lattice parameter measurement due to the image-based distance measurement and the potential error. More accurate due to the high resolution, unable to provide the crystallographic information, only suitable for the amorphous material. C is no. Unable to provide crystallographic information, it do provide crystallographic information. More accurate due to the high resolution. C. Now what we are talking about, I should specify here from the perspective of lattice parameter measurement. When we are talking about the lattice parameter measurement, which technique you should use? Whether you should use TEM or you should use XRD. The right answer is XRD, not the TEM. Now, let me tell you the reason. The reason is something which we have already discussed. See how you will find the lattice parameter. See here also we have found the lattice parameter. To find the lattice parameter, what we should know? We should know the value of R. How you will get the R? You got some image. Around that you will get a ring. And ring will always be a little bit of diffuse only. So in that case, if you try to find the distance, a different person can find a different distance. A small error will always be associated with it due to the way, like the method by which we are doing this. Image-based approach. So image-based approach will give us the precise lattice parameter will not be obtained. Error will be associated with that. While XRD is not the image-based approach. So that's how you should use the XRD. So one can ask me that under what condition I should use the TEM for the lattice parameter measurement. For example, you have the composites and you want a particular region only to see what is the lattice parameter happened, what happened to that particular lattice parameter of that particular region. In that case only you should use the TEM. If you want precise, and if you have like, okay, I want the generalized XRD pattern, so you generalize the lattice parameter, what is the lattice parameter of the entire specimen, you should use the XRD instead of TEM. So the right answer here is option A, less accurate for the precise lattice parameter because due to the image-based distance measurement and the potential error. Okay, this is how we have solved the question number 21, and with that our like number of questions are over. Now I would like to ask you, like, if you have any doubt whatever we have discussed today or whatever that has been discussed in the class, or any difficulty you are facing, let me know. Yes, Amit.
Yeah, here, in assignment question, always the options are not there for the mathematical question. It's the same way that exam also will be there, or examination in mathematical question option will be available.
Actually, we are. I already wrote a mail. I'm waiting for the response, like when and all the assignments we can correct, and the error which is already there, which the mistake which have already happened. For that, what we are supposed to do. So for that, let's see. Let's wait for a week. Maybe I am expecting the reply by the next week. And for the assignment, like for the exam, your this particular question is also this. is also very important. So I will try to raise it in the meeting if there is any. If I am able to conduct any meeting with the professor or NPTEL team, I will try to raise that, so that before exam also, before it happen, before they set the paper, we should rectify it if there is any error associated there. So rest assured, we'll get the answer. I'm more positive that we'll get the answer by the next week, and whatever the has mistake has been done, we'll try to rectify that. Uday is asking that the exam will be objective type. See, it will be the computer based exam. It won't be the pen paper based exam. Now, whether it be the objective and subjective, that will be a little bit difficult to tell, because there will be some question can come where you have to type the answer, but it won't be too much. Okay, it will be little bit only, straightforward type of questions only. You don't have to describe anything in the brief and all. Okay, so more or less you can expect to be the mix. I would suggest you that, okay, I would, from my point of view, like I have also appeared in the couple of NPTEL exams. More or less, they are inclined toward the subjective type. Sorry, objective type. Okay, yeah. Yes, guys. Any more doubt? Okay, since there is no doubt, let's move to the, like, we can conclude this particular week, and we can meet again in the upcoming week, same time, same date.
Here one more question I
Yeah,
have. Because each week's content there is a 5 videos is there. That same 5 videos will be continued until 12 weeks, or there is any reduction will be happening in the upcoming weeks. Yes, I have did a couple of NPTEL exam also.
uh-huh.
That each week contain three lessons only. But this is the first time I am facing that continuously each week having 5 continuous videos. Um, it's a little bit burden or overload to me compared to with examination.
I see.
It is
Yeah, I agree with you. Like, there are the few courses which I did. Those there were the courses which are having even more than the 5 lecture also per week. They are having the more. So it is free up to the professor how they want to conduct the class. So it's the freedom is absolutely given to them. So based on the content that is needed to be